Hey class, Mr. Houston here, and today we're talking about Chapter 12, Lesson 5, Probability of Independent and Dependent Events. First thing I want to talk to you about is what the difference is between independent and dependent. Okay, so you children are dependents, meaning that you rely on your parents for whatever, housing, food, all that kind of stuff, whereas independent is like when you move out on your own and you're not dependent or you're not relying upon anyone else. So that plays a big role in our probability here today. So example number 1, we're just identifying independent or dependent event. Jar contains red and blue marbles. You randomly choose a marble from the jar and you do not replace it. Then you randomly choose another marble. Tell whether the events are independent or dependent. So the question becomes does your second marble choice depend on your first marble choice? In this case, the answer is yes, because you're not replacing that marble. That makes it a dependent event. Okay? So when your second event can be influenced by your first event, that becomes a dependent event. If I were to put the marble back, then that becomes an independent event because your odds will be there, or your probability will be the same for either of them. All right, so last two formulas here. Instead of adding, now we're going to be multiplying probabilities together. All right, so independent events, you just take the probability of A times the probability of B. Dependent events, you take the probability of A times the probability of B after A has already been taken out. All right, so let's show what that looks like. So first is probability of an independent event. So as part of a board game, you need to spin the spinner at over here, which is divided into equal parts. Find the probability that you get 25 on the first spin and 50 on the second spin. So this is an independent event, 1, because I tell you that, but 2, because you're just spinning a spinner. It's not like what you spin disappears after you are done with that. So you are trying to find the probability of a 25 and then a 50. So what's the probability that I will get a 25? There are 2 on here, and there are a total of 8 on that spinner. So the probability of a 25 is 2 out of 8. The probability of a 50 will still be out of 8, and there is only one of them. So 1 out of 8. So we will then just multiply. Remember to multiply straight across. So we will get a 2 over 64, and that will simplify down to 1 over 32. So you have a 1 in 32 chance of spinning a 25 on the first spin, 50 on the second spin. All right. Now, probability of dependent events. So a bowl contains 36 green grapes, 14 purple grapes. You randomly choose a grape to eat, and then you randomly choose another grape. Find the probability that both events A and B will occur. And some information that I left off here. Event A is that you eat a green grape, and event B is that you eat a green grape. So we will say the probability of green, then green. So our first probability, how many green grapes do we have? We have 36 green grapes. We have a total of 50 grapes altogether. Now when we go to event 2, you have already taken one and eaten it, so we are down to just 49 grapes, and you're operating under the assumption that your first grape that you chose was green and that you ate it, so you are down to just 35 green grapes. So you will multiply those two together, so 36 over 50 times 35 over 49, and you will get 18 over 35 as a simplified answer. Okay? So understanding dependent events is that second probability will be reduced at least by 1 at the bottom, because whatever it is you're doing, it probably will take one away. And in this case, the key here is that we were eating a green grape first, so that's why our top number went down as well. All right, go ahead and flip on over to the back. Let's take a look here at Example 4, the table shows the number of tropical cyclones that formed during the hurricane season from 88 to 2004. Use the table to estimate the probability that a future tropical cyclone in the northern hemisphere is a hurricane, and the probability that a hurricane is in the northern hemisphere. So the first one is, we need a tropical cyclone in the northern hemisphere is a hurricane. And then we'll do part B when we're done with part A. So in looking at this, we need to determine type of tropical cyclone in the northern hemisphere is a hurricane. So we're looking here. So we'll talk about A, probability of a hurricane. And there were 545 hurricanes in the northern hemisphere. Then we need to figure out how many tropical cyclones took place in the northern hemisphere. So you're just going to add all those up. 545 plus 398 plus 199 will give us 1,142. We'll simplify that fraction, and we will get, we can't simplify it any further than that, so maybe we'll give a percentage on this one, so that would be a 0.48 as a decimal, which is also a 48% chance that the next tropical cyclone in the northern hemisphere is a cyclone. Okay? Either any of these three would be acceptable as your answer. So let's take a look at B. Probability that a hurricane is in the northern hemisphere. So now we're looking strictly at hurricanes. So B, probability of a hurricane, and we'll just put in the northern hemisphere, would look like this. It'd still be 545, that's how many took place. But then instead of adding up just the northern hemisphere, we're going to add up with the southern hemisphere. So that would be 760 total hurricanes, 545 of them coming from the northern hemisphere. So 545 with 760 simplifies to 109 out of 152, which would give us a 0.72 or a 72% chance of occurring. So 72% of the time, if it's a hurricane, it's happening in the northern hemisphere. Okay? All right. Example 5, you randomly select 2 cards from a standard deck of 52. What is the probability that the first card is not a heart and the second card is a heart? So part A is you are going to replace the first card before doing the second, and then part B will be you're not going to replace it. So let's talk first about part A. We're finding the probability of a heart. Not a heart, and then a heart. So not heart, then heart. So probability that the first one is not a heart, there are 13 hearts in a deck. There are 52 total cards in a deck. So there are 39 cards that are not a heart in a deck. And then you are replacing, so we still have 52. And in this case, we want a heart, so there's 13. So 39 over 52 times 13 over 52 gives us 3 over 16. And since we've done this before, that's 0.1875, which is an 18.75% chance. Okay? Now, we're going to see what we do when we don't replace the card. So we're still doing the same thing. So not heart, then heart. So probability the first one is not a heart, is still 39 over 52. Now this is going to go down by 1, so we're down to 51. But we're not choosing a heart the first time, so it's not going to affect our top number. So top numbers will be the same, bottom numbers will not. We multiply those together. You get 13 over 68. Which, when you change that to a decimal, you'll get 0.1191, which is at 19.1%. Okay? So make sure you really understand the difference between not replacing and replacing. Not replacing is dependent, replacing will make it independent. Alright, last but not least, using observations made of drivers arriving at certain high school, a study reports that 69% of adults wear seatbelts. High school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt. Alright, so we created this chart from that information up there. So as we can see here, 69% of the time an adult wears a seatbelt, meaning 31% of the time the adult does not. And then from there, 66% of the students wear a seatbelt, which means 34, and then so on and so forth down here. So what they're asking for us here, what is the probability that a high school student in the study wears a seatbelt? So in order to do this, you are going to have to do a couple of different things. We are trying to find the probability that a student wears a seatbelt, and it appears twice. So in order to find the probability of event C, we're going to have to take the probability of A and C, and we're going to have to add it to the probability of B and C. In order to do that, we are going to have to multiply the percentages together. So for event A, for this one, it's going to be 0.69 times 0.66. So I don't need that there. So that one would be 0.69 times 0.66. Then down here, 0.31 times 0.26. So when we multiply those together, the first one is 0.4554, and the second one is 0.0806. So when you add them together, you get 0.536. So 53.6% of students wear seatbelts. So I threw a lot of information at you here today with probability, independent, dependent events. I encourage you to go back and look at any parts that don't make sense, read them again, watch again. If you have any questions, bring them with you to class, and we will see you then.